All right, this problem is about a pressure relief valve. These are valves you put in a fluid system to keep the pressure from getting too high. If the pressure gets too high, they open and the fluid spews out. So this relief valve, we're designing it, it looks like this. We have a column of water here or fluid. We can put in more or less, and we're seeing when it will force this thing to open. So it's a little circular disc being pushed down by a spring that's pushing against the fluid. That's the idea. So we have the spring constant, we have the diameter of the disc, we have how much the spring is displaced, we can figure out how hard it's pushing down. We want to test it, we want to attach it to this column of water, and at what height will the valve open? Meaning as we add more and more water, this fluid level goes up, when will it eventually open that valve? When will it push the disc up? So it will open when, and you can decide if you want to do this with forces and kinematics or just do it with pressure. There's two ways to think about it. When the sum of the forces in the y becomes greater than zero, when there's suddenly a net force pushing up. Or you could say when the pressure from the inside becomes greater than the pressure on the outside. Meaning the pressure of the fluid pushing up on the disc is greater than the pressure of the outside pushing down on the disc. So since we're doing fluid mechanics, let's think of it that way. So let's see. The pressure on the inside is the fluid pressure right there. And at first you think you don't know that, but then you remember you can draw a horizontal line, and that's equal to the pressure right there. Right? And we get the pressure there because we just have a column of water at some height that we're looking for. So let's see. So let's call how high this column of water above this 12 centimeters is. We'll call that H. Okay. So we'd say then the pressure right there is the P naught. In this case, P naught is atmospheric pressure plus rho GH. Right, the density of the water, 9.8 for gravity, and then the height of the column. And in this case, that's why I chose this to be H. That's exactly the pressure to right there, not all the way to the bottom. So we want to know, when is that going to be greater than, or we'll say when does it grow so much that it equals the pressure on the outside. So on the outside, you've got the spring pushing down. So it's basically, you get it by saying it's the force of the spring per unit area. So you just turn the spring force into a pressure. But also, atmosphere is pushing down on that disc. I mean, just like it's pushing down on the circular surface of the water, it's pushing down on the disc. So we actually do have to add atmospheric pressure in there as well. So the atmosphere is pushing on both sides. It's really just going to be the pressure created by the water column that matters. Because you can see we're just going to cancel that. Those are the same on both sides. All right, so let's see what we know here. 1,000 is the density of water, 9.8. Gravity. H is, I think, what we're looking for. We were asked at what height will the valve open? Yeah, so we need this H. It actually, I think, numerically it wants on the axis, so we'll add 12 to it later. But for now, we'll just call it H. Equals the spring. Well, we know it's spring constant, and we know how much it was deflected. Right? So its natural length is here. It was pushed up by a centimeter. So we just use Hooke's law, F equals Kx. So it's 2123.01 K delta Y, or whatever the deflection of the spring. That 0.01 is that 1 centimeter. And then the area of the thing is pi, everything in MKS here, 5 centimeter diameter, right? Yeah. So 0.025 is the radius. Right. That's it, because we took away the atmospheric pressure. So we need to now find H, and I get 110 centimeters. So it's going to be way up there, 110 centimeters before it'll make enough pressure to open that valve. But we weren't asked for H, we were asked for the Y position. So we're going to add the 12 there to get Y equals 100 and what is that, 22. Thereabouts. For our online homework system at Rice, this one was made with random numbers, so you'll have different numbers.